So when we have the paired electrons, this shows the zero magnetic moment, so they are basically magnetically neutral. But when we approach with a magnet for any pair electrons, and then any couple of electrons who are rotating in the opposite direction, then also we will be able to see some sort of magnetic behavior in the pair electron atoms. Now for the unpaired electrons, they are initially have they from the beginning they have kind of magnetic moment which is not zero basically, and we can easily experience a magnetic behavior for the unpaired electron atoms. So what we have learned in the paramagnetism, right? So now in the ferromagnetic substances, they have the non-zero magnetic moment and also the unpaired electrons, and also they are most likely in the solid state. So in the periodic table we have four element who behave like a very strong ferromagnets. For example, the iron, Fe, then the manganese, then nickel, and then gallium, right? So these four elements shows a strong magnetic behavior in the periodic table, and they can be converted to a very strong magnet by application of electric current or external magnetic field. And these effect only have been observed in the iron at the very beginning. So that's why ferromagnet named as the ferromagnet. The first word of the ferromagnet comes from the iron itself. All right, so now what kind of structure you can expect inside of any ferromagnet. So if you look at any ferromagnet inside of the ferromagnet, so then in the previous case we have showed you that any given arrow, if we just draw one arrow, and this arrow head if indicates the north pole and the tail indicates the south pole, then you will be able to see that inside of the iron there are other strong ferromagnets, and then you will be able to see that the non-zero magnetic moment, they orient in a particular direction in one if you let me draw, and then you'll be able to see. Let's say for example, this is the direction of magnetic moment, or you can say in other words the north pole. So now if I ask you what is the basic difference between the paramagnetism and the diamagnetism, then you'll be able to see that then a group of magnetic moment or a group of unpaired electrons, they orient in one particular direction, and we name them as magnetic domains, right? For example, this is one domain, the net magnetic moment directed in one particular direction. Now this is another domain. For example, this one is another domain. So now you can call this one also another domain, and this one also another domain. Now this all the domains, they have the net magnetic moment, but they are not oriented in the proper order. So that's why they do not show a magnetic property, because all the magnetic moment does not orient in one particular given direction, right? So now if this ferromagnet is exposed inside of a strong external magnetic field, now how they will behave? Okay, for example, let's bring one bar magnet in front of this ferromagnet, right? So let's say this one is the north pole and this one is the south pole. Now as we know and as we have seen that the magnetic lines of force will emit from the north pole, and it will penetrate the ferromagnetic substances, and it will basically, what will happen, we'll be able to see that all the south poles of this particular inside of this ferromagnet, they will orient in such a way that all the south poles will be attracted towards the north pole of the bar magnet, or in other words, in the direction of the magnetic field, all the north pole will align themselves. So if I draw again the this ferromagnet, then you'll be able to see that all the dipoles, they have arranged themselves in a regular pattern, right? So this is basically the pattern you can expect when you expose one ferromagnetic substance inside of external strong magnetic field, and we expect that this external magnetic field is very strong. And now in the presence of external magnetic field, the internal magnetic field that also generates, and we can name it B. So now there is an equation which is basically bridge them between B and B naught, and this equation is given like in this way: B equal to mu r into B naught, where B naught is the external magnetic field and mu r is the ratio, which is different for different ferromagnetic substance, right? It depends on how much, what is the intensity of the external magnetic field which you are applying to get the magnetic field which is desired magnetic field in the inside of the ferromagnetic substance, right? So this is the equation, very basic equation. Now the interesting point arises when the question comes that when we switch off that external magnetic field, what will happen with the internal magnetic field what that ferromagnet has generated. Now there are you can just pause the screen and take one guess, take one quick guess, and you can tell me that what would happen. Most of you would say that this magnetism what this ferromagnet has developed inside of itself, it will go away, it will become it will fade away, right? So because most of you would say that this ferromagnetic substance again come back to the random shape, okay, like before, in the absence of the external magnetic field. And a few of you would suggest that a couple of dipoles will also after the removal of this external magnetic field, a couple of dipole will also stay like as it was in the very first place. And for that case, like there will be a non-zero magnetic field also last after the removal of the external magnetic field. That is also some of you will say. Now based on that, all the ferromagnetic substance can be divided into two categories. Number one is the hard. Number one, the first category is named as the hard ferromagnets, and number two is called the soft ferromagnets. Okay, so the hard ferromagnets and the soft ferromagnets. What do we mean by the hard and the soft ferromagnets? The hard ferromagnets are those who after the removal of external magnetic field still shows the magnetic property inside of its domain. That means all the domain does not deliberately come back to its original random spaces. They also, after removal of the external magnetic field, they stays as it was when there was an external an external magnetic field, right? For example, you can say that you can call this hard ferromagnetic substance as the obedient child, right? So obedient child, after the teacher move away from the class, they also behave like an obedient child. So this is you can say that the hard ferromagnets, they are basically obedient child. And in other words, like in contrast with that, the soft ferromagnets are those who after the removal of the external magnetic field, those who come back to its original normal state or normal random position, that all the dipoles again orient themselves in different direction, any given random direction. We can call them the soft ferromagnets. It does not we are not saying that the soft ferromagnets are very like cushion or something like that. So this is funny basically, but what we essentially mean is that the amount of magnetic moment which will generate in the presence of external magnetic field will disappear the moment when we remove the external magnetic field. All right, so let's quickly go to the hysteresis curve now. Here comes into play the hysteresis curve. Let's say, for example, the left hand side of the diagram represent the hard ferromagnet and the right hand side of the diagram represent the soft ferromagnet. If it is so, then the after the removal of external magnetic field, how they will behave, it depends on the hysteresis curve. Now what is hysteresis curve? So hysteresis ISIS curve. All right, so now we'll talk about the hysteresis curve. So now what is basically and essentially a hysteresis curve? So after the removal of the external magnetic field, you cannot deliberately say that the north pole, all the north pole will come in this side and all the south pole will come in this side. Yeah, this is a confusion, this is a point of confusion. You will definitely say that for the hard hard ferromagnets, it is definitely this side will be north pole and this side will be south pole even after the removal of the external magnetic field. But you cannot deliberately say for any ferromagnetic substance without knowing the hysteresis curve. Now what is hysteresis curve? The hysteresis curve basically represent the history of this ferromagnet. the history this ferromagnet has went through. If you do not know the history of this curve, you won't be able to tell whether this side will be north pole and this side will be south pole or not. All right, so how can you tell that which side of this ferromagnet will become north pole or south pole? It depends on the curve itself. So let's quickly draw the curve and let me go you through the understanding of this hysteresis curve. This is very interesting. Let me draw one axis. Okay, so let me draw here. We are taking a large space because we need to draw the diagram so that you can understand the point, so what we are trying to explain. Okay, so this hysteresis curve is basically based on if we draw, for example, here if we draw along x-axis, if we take the B naught or the external magnetic field, and along y-axis if we take B, that means the field inside of the ferromagnets. Okay, so then what would happen if we increase this external magnetic field? Then how the internal magnetic field will change? Okay, if I ask you, then you will definitely say that so internal magnetic field will increase. Internal magnetic field will start increasing when you increase this external magnetic field, right? So what we essentially mean is that if this is a ferromagnet, so if you increase this external magnetic field, for example, this is external magnetic field, so if you increase the external magnetic field gradually, then gradually one by one all this magnetic moment started orienting themselves in the direction of the magnetic field, right? So internal magnetic field will start increasing as soon as you increase the external magnetic field. The more external magnetic field, the more internal magnetic moment started orienting themselves according to the external magnetic field. All right, so the curve will go in this way, right? But after a certain time, after a certain period of time, when all the internal magnetic moment oriented themselves in the proper order of the external magnetic field, then there will be a saturation. That saturation means after this saturation, there will be no more magnetic moment will left out to orient themselves according to the external magnetic field. So that means this curve will reach up to after a certain point, it will reach a saturation. Okay, so this is the saturation point. So if we draw one straight line over here, so this straight line will cut at some point over the B axis, and we can call them that B saturation, right? So this is the maximum magnetic field we can get out of this internal ferromagnetic substance. So now let's say we are taking that one cylinder, for example, right? So one cylinder we are taking. So this is the cylinder we are talking about. This is the ferromagnetic substance. Now we are applying the external magnetic field, and in order to do that, what we are doing, we are supplying some current. So in order to supply the current, what we are doing, we are making a solenoid. This is the basic idea of making one magnet, right? So we are making one solenoid and wrapped around this ferromagnetic substance, right? So now the solenoid, there is a power source, right? There is a power source and there is a key, right? So now the moment when we send current through this particular point, then what will happen is that there will be an external magnetic field, and which is basically stronger in the core of this solenoid, right? So there will be an external magnetic field. So this magnetic field depends on the amount of current which we are sending, right? So as soon as there will be current in the external circuit, this ferromagnetic substance or the cylinder will experience external magnetic field, and when it will experience external magnetic field, the internal magnetic field will start increasing, right? And after a certain point, it will hit this B saturation, and this B saturation means that all the dipoles, they have oriented themselves in the proper order, or in the proper order of the external magnetic field. So we are drawing a tiny symbol over here, right? And which is basically, we are indicating three small magnetic moment of the dipole in the proper order, and which is basically indicating that all the magnetic moments are oriented in the proper order, and there are no more magnetic moments which are left in the opposite order or in the other order, right? So this is the maximum point. This is the maximum magnetic field we can get outside of this ferromagnetic substance. Now what would happen if we now decrease the external magnetic field? Okay, so we are going from 0 to positive side of the x-axis. Now we are coming back. So as we are coming back, if you can see, so as we are coming back, or we are coming in this direction, what would happen? You'll be able to see that the magnetic moment started so decreasing. So magnetic field will start decreasing inside of this ferromagnetic substance. So basically the magnetic moment start decreasing, and at some point it will cut the y-axis. Now what is this point? So you'll be able to see that the curve is going in this direction and curve is coming back in the some other path. What does that mean is that the curve is not going back to its original state with the zero magnetic internal magnetic field, but it is hitting at some point in the y-axis, and this indicates that even if you switch off this circuit, or if you don't send any current, and there will be no external magnetic field, or the external magnetic field is zero for this case, for this particular point, then also we can expect some amount of magnetic field inside of the ferromagnetic substance, and we can call is the tension, the property of the tension, or holding the magnetic moment which will be non-zero. Okay, so we can expect a magnetic effect out of that ferromagnetic substance once we convert this into a magnet, even if the external magnetic field is zero. Now you can expect that if you draw one cylinder over here at the retention point, then we'll be able to see that at least one or two dipoles, they are still oriented in the same order. The magnetism has been decreased, that is true, but it has not been, it is not zero, it's not completely zero. So in order to make this ferromagnet like it was in the beginning, or the net magnetic moment zero, in order to make this net magnetic moment zero, we need to apply some external magnetic field in the opposite order. So how can we do that? How can we expose this ferromagnetic substance in an external magnetic field which will occur in the opposite order? This is very simple. Just do one thing, just change the orientation of the current here. Okay, so if we just change now, let's say for example erase this one, okay, and then just plug this one negative and this one positive and send current through in the opposite direction. Okay, and definitely close the switch. If you do that, then the direction of the magnetic field will immediately change. Okay, so let me erase the magnetic field direction. Okay, magnetic field direction. So if we now just send the current in the opposite direction, then the net magnetic field will be coming from this side, and it will emit from this side, right? So it will emit from this side. So as we can see that we have changed the direction of the external magnetic field, then what we can expect is that this external magnetic field will try to neutralize the internal magnetic field, and this curve will come back. At some point over the x-axis, it will become zero. And what does that mean is that if we draw this at this point, all the dipoles, those who are in the opposite direction, they will basically nullify the effect of internal magnetic field, and there will be no external there will be no non-zero magnetic moment exist inside of this ferromagnetic substance. Now what will happen if you now further increase the magnetic field, the external magnetic field, to some extent in the opposite direction? Then this curve will still will take. Okay, so yes, we can use the red color. The red color will indicate that we are going below, or we are creating the magnetic field which is basically in the negative order. At some point, this curve will hit the saturation. This curve will hit the saturation because all the dipoles, all the magnetic moment will orient themselves in the opposite order again, and we have a limited number of dipoles inside of the ferromagnetic substance, so it will again hit the saturation point, and we can name them as B saturation, but this one is in the negative or in the opposite direction right now. So now again, if we just start decreasing this magnetic field, the external magnetic field, or the amount of current we are sending, then this curve will again come back and it will hit some point over here, and this is basically the retention point. I told you this is the retention point, right? The amount of retention, we can call it the retention point. Okay, so yes, we need to draw two more diagram over here. So here is basically the solenoid, and all of the magnetic moment, they are oriented in the opposite direction. By three magnetic moment, we are expressing that all of the magnetic moment, they have oriented themselves in the opposite direction. Now at this retention point, we can draw this one where at least two magnetic moment, they have oriented themselves in the direction of the external magnetic field. Okay, now if we further decrease the amount of current, sorry, in this particular point, after the point, reaching the detention point in the opposite direction, if we now change the current in the proper order, in the likewise in the previous order, then what will happen is that this curve will start increasing, and it will now go back to saturation again. Okay, and it will follow the same curve. Now you can see that the length of this line, if you now see, this length of this line is called the detention strength of the ferromagnetic substance, right? So this is the detention strength in the opposite and the positive and the negative detention of any ferromagnetic substance. The more fat this graph will be, the more retention it can take. It can take more. It can hold more amount of magnetic moment, non-zero magnetic moment, after even removal of the external magnetic field. So you are getting my point, right? So yes, now if I ask you, so at some one given point, this magnetic moment or the external magnetic field, after the removal of the external magnetic field, the ferromagnetic substance can show the north pole is in this direction and south pole is in this direction, and also it can show north pole is in this direction and south pole in the opposite direction. Okay, so it can also possible. So you cannot deliberately say that after the removal of any external magnetic field or external magnetic field, or this for this electromagnetic the current, you cannot deliberately say that this side will be north pole and that side will be south pole. You need to know the history of this particular material which it is basically going through, and you need to then you need to check the hysteresis curve, and then you need to tell that why this side will be north and opposite side will be south or not. Okay, you need to verify the hysteresis curve. All right, so now what is this that thickness of the curve basically representing? If you look at this curve, then the area under this curve, the area, whatever the area we have inside of this curve. So if we look at the area under the curve, if you look at the area under this curve, so we have shaded the region inside of the area of the curve. The area under the curve is representing the amount of work done needed to convert one ferromagnetic substance into a magnet, basically. Okay, so what do I mean by the work done? So work done means that the work done we need, the work done we essentially need to convert all these magnetic moment into the proper direction. Okay, so for example, this is the external magnetic field, you can see B naught. Now we are, when we are orienting any magnetic moment, like this is the magnetic moment, and we are orienting in the proper order inside of the ferromagnetic substance with the presence of any external magnetic field B naught, right? So basically when we are orienting this external magnetic moment in the proper direction, then we need to do some amount of work. This work done stored as energy, because this is a conservative force field. So definitely all this work done we will do with the help of the external magnetic field. This work done will be stored as energy inside of this ferromagnetic substance. So this energy basically we need, or the heat energy we need by the external agent to to rotate all this magnetic moment in the proper direction, is basically indicated by the area of this curve. So what would happen, what we essentially mean by the hard and the soft soft ferromagnets. Now the hard ferromagnets, and this will, okay, so let me draw one more diagram over here to make you understand. So for the hard, let's say this one is one graph. Now this one, okay, this one is one, and the second one is this, and let's say this one. Okay, so if you look, if you just verify these two hysteresis curves, then you will be able to see that the area under the curve for the A and area under the curve for B, they are clearly different. And what does that mean? This one is called the hard ferromagnet. This one is called the hard ferromagnet, and this one is called the soft ferromagnet. Now, why this is hard and this is soft? Because we know that in the hard ferromagnet, we need to do a hell lot of work, or the external magnetic field has to do a lot of work to convert or to orient the the internal magnetic moment in the direction of the external magnetic field. So that's why the area under the curve is very large. Now in this case, for the soft iron, for example, like molten metals, for example, the soft iron cores, this is kind of like soft ferromagnets basically. So in terms of when we are dealing with the soft ferromagnets, they are not essentially has to be soft and physically you need to, like, this is a cushion and you can press that. This is not the case, but inside of the molecular structure the electron can rotate in the different direction, and we can do that easily for the soft ferromagnets. And that's why the external magnetic field do not, don't have to be. So in the external magnetic field, it do not so for the soft ferromagnetic substance, the external magnetic field, they do not perform a lot of work in order to convert this soft iron or soft ferromagnet into a permanent magnets. All right. So basically, the area under the curve is very small, and also if you look closely, then you will be able to see that the retention line is very thin. But if you look at here, the retention line is very large. That means in the hard irons or in the hard ferromagnets, there are a lot of retention even after removal of any external magnetic field. But in the other words, when the soft ferromagnets we have, by checking the hysteresis curve, we can say that after the removal of any external magnetic field, we'll be able to see at least almost there are no magnetism left inside of this ferromagnet. Although the magnetism will not become zero, because you can see that if you zoom in, then you'll be able to see that these lines are not touching in the origin. So that's why the total magnetic field will definitely not be zero, but it will be close to zero. That means few couple of magnetic moments still orient in the direction of the external magnetic field in the absence of any external magnetic field in the soft iron core itself, right? But it will not become exactly zero, but it will be close to zero. And as the area of the curve is very thin, what does indicate is that easily we can convert any soft ferromagnet into a magnet, and easily we can come back to the zero magnetism once we remove the external magnetic field. And in other words, the hard ferromagnet, it is very hard, or it is very we need to do a lot of work to convert one hard ferromagnet to convert into a magnet. And then if we remove the external magnetic field, then we will be able to see a lot of retention of the internal magnetic field inside of the ferromagnet. Okay, so this is all for the ferromagnet, and in the next class we'll discuss about the retention.